Hey everyone, welcome to my video. The demonstration at the beginning showcases a control master I designed for remotely operating the robotic arm. While the results may not be perfect, the functionality is there. Let's briefly talk about master-slave operation. Feel free to skip this part if you'd like. Master-slave operation, also known as teleoperation, is a technique that allows a user, the master, to control a robotic device, the slave, located remotely. The operator interacts with the robotic arm through sensors and actuators, enabling precise task execution. Compared to the traditional programming methods used for industrial robots, the main challenges in teleoperation are real-time control and environmental awareness, commonly referred to as force feedback and visual feedback today. Real-time control requires high-frequency data exchange between the master and slave, which places high demands on communication. Additionally, the robotic arm must exhibit high dynamic responsiveness. The development of teleoperation technology for robotic arms spans multiple disciplines, evolving from early basic mechanical design to today's complex robotic systems. This evolution involves fields such as computer science, control engineering, and sensing technology. The concept of teleoperation can be traced back to World War II and the early post-war period. After the war, the US needed a safe and efficient method for handling nuclear materials. Early robotic arms primarily relied on mechanical drive systems and simple electrical controls, without computer assistance, depending largely on direct human operation. As electronic technology and control theory advanced, robotic control systems began to incorporate electronic components, transitioning from purely mechanical operations to electric control. Key technologies during this period included motors, sensors, simple logic control circuits, and rudimentary feedback control systems. In more recent times, robotic arms have increasingly relied on computer control, utilizing microprocessors for complex path planning and control. Thanks to advancements in the semiconductor industry, computing chips have become smaller and more powerful, while various sensors have also significantly miniaturized. This progress has allowed for the integration of force sensors and position sensors, enabling more precise operations by the robotic arms. With the advancement of communication technology, teleoperation applications are no longer limited to ground-based scenarios. They can extend into space as well. The development of contemporary artificial intelligence and machine learning technologies has opened up even more possibilities for teleoperation. The multimodal fusion of visual, tactile, and force sensors allows operators to perceive and understand complex environments without being physically present. Next, let me give you a brief overview of my master-slave system. First off, all structural components of my robotic arm are 3D printed, which means the rigidity is quite poor. My initial goal in creating this robotic arm was simply to learn embedded systems, so I didn't check factors like motor torque, inertia ratios, or dynamic response during the structural design phase. For basic teaching functions, those requirements aren't very high, but for real-time teleoperation, the motors need to have very high acceleration. If the arm had better performance, the results would be significantly improved. Unfortunately, in its current state, I can only achieve basic functionality. Both the structure and motor output torque are lacking. In the future, if I design something more substantial, I'll definitely consider multiple factors from the start. Now, regarding the logic of the master-slave operation, my setup involves a master hand that differs structurally from the robotic arm, which means it's a heterogeneous master-slave system. The process works like this. The master hand uses encoders to collect the absolute angles of the links and applies forward kinematics to determine the current hand posture, including the end effectors X, Y, Z coordinates and the Euler angles around those axes. If you're unfamiliar with this, a quick online search will help clarify. Once the forward kinematics is complete, the position information is transmitted to the robotic arm slave side via a communication method. Currently, I'm using simple wired serial communication, but wireless communication is certainly possible, as 2.4G Wi-Fi can easily support this. After receiving the position data, the slave side performs inverse kinematics to control each joint, enabling the robotic arm to mimic the movements of a human hand. An object in space has 6 degrees of freedom, so to fully define its orientation, you need 6 input variables. Let me give you a brief overview of my master hand structure. It's quite simple and resembles the layout of a palletizing robot. The key feature of palletizing robots is that they place the power input at the base to reduce the load on the end effector. Similarly, I've positioned 3 encoders at the base mainly for easier wiring. These encoders collect the rotational angles of the base and the 2 links. Additionally, there's an encoder at the handle to capture the tilt angle. The last 2 input variables are derived from an IMU, inertial measurement unit, located inside the handle, which is the same type commonly used in balancing robots. This IMU captures the roll and pitch angles. There's also a pinch clamp at the handle, which uses another encoder to collect rotational angles. The clamps gears are coupled, with a spring in between to provide a synchronized gripping effect through rebound. To reduce friction, I've incorporated bearings within the overall structure. For more specific details, you can check out the model. Now, moving on to the hardware part, the Master Hands hardware is also quite straightforward. The main control unit is an ESP32C3 chip, which has an AS5600 integrated on the board to detect the angle of the clamp. All other encoders also utilize AS5600. However, there's a challenge with the AS5600. It communicates via I superscript 2C, and the address is fixed. To solve this, I've used a TCA9548A I superscript 2C multiplexer module to enable multi-channel communication on the same address. Additionally, I've routed several PWM input ports, which can be used to connect potentiometers or other components that rely on resistive voltage division. To wrap up the video, I want to emphasize that building a robot is not an easy task. Initially, I approached it with a fearless attitude, but as I got deeper into the project, I realized that designing the structure and creating the hardware is just the first step of a long journey. For the same robotic arm, optimizing algorithms can significantly enhance performance. For instance, I initially didn't apply any filtering on the Master Hand, resulting in severe jitter. I also neglected to properly tune the PID parameters for the motor drive, which led to excessive acceleration and further instability due to the arm's low rigidity. While I've managed to implement the functionality through algorithms, there's still a lot of room for code optimization. Streamlining the code, improving execution efficiency, and increasing the motor's position refresh rate can greatly enhance the real-time responsiveness of the master-slave control. The path of learning is full of challenges, but I'll keep progressing. Stay tuned for more updates.